Hello and welcome back to your next lesson. So today, still working with numbers and we're looking at proportions. So last time we was mostly focusing on, whole numbers. So now we're looking at fractional values or decimal values, percentages, that sort of thing. So the lesson plan for today is essentially that. We're seeing like how do we work with these different types of proportions and how do we convert between them because as we'll see, uh, each one has a different purpose really. So we're going to begin with fractions. So fractions, what kind of things can we do with fractions? So, first things first is how can we simplify fractions? This is something we're constantly doing in mathematics. We always want to make things as simple as possible. So when we have a fraction like this, how do we simplify that? And in this case, simplifying means to make the numbers smaller. And how we do that is by looking for a common factor on the numerator and the denominator. So the numerator is the top number of the fraction, denominator is the number at the bottom. So in this case, we can see the common factor being 5 because 15 is 3 times 5, 65 is 13 times 5. And we can then essentially split that out, take the 5 by 5, 5 over 5 by itself. And the thing is, why we look for common factors like that, because 5 divided by 5 is basically 1. And if you're multiplying by 1, it doesn't change anything. So this will basically just be 3 over 13. So that's how we simplify fractions. And in order to do that, we need to look for common factors. And to do that, we can use certain things known as divisibility rules. So if we want to know whether or not a number is divisible by another number, certain common numbers, like smaller numbers, we have common rules for them. So say like here, if we want to divide a number by 2, any number that's even, so if the last digit is divisible by 2, the whole number is going to be divisible by 2. Um, or if we have a number that ends in 0 or 5, it's going to be divisible by 5. If we have a number that ends in 0, like we've seen last time, that means it's going to be divisible by 10. It's got a factor of 10 in there, which we could then also split up into a factor of 2 or a factor of 5. Um, and then we've got some that are not so obvious, like this one. Like, say if you add up all the digits of a number together, you and if that's divisible by 3, then the whole number is divisible by 3. Um, and then we have one for 11 as well, which is a bit more cumbersome still, where you add every other digit. Like I've given a little example here, and you find the difference between those two sums. And if that's divisible by 11, the whole number is divisible by 11. You might not need that one so much, but the others to divide by 2, 3, 5, 10, they're really important to know. Um, and sometimes we want to, like here, I would make the numbers smaller. Sometimes we want to make them bigger, and you'll see that when it comes to adding fractions. So, say here, if we wanted to get that denominator to 63, for example, well, we can times 7 by 9 to get to 63. And as long as we do the same thing to the top as well, the fraction will remain the same because you're essentially times it by 9 over 9 here. And 9 divided by 9, again, it's 1. And if you're times by 1, it's not changing anything. And so that's why that can work. You can scale numbers up or down as long as you do the same to the top and bottom. So let's look at some arithmetic with fractions. So we've got, say, multiplication. Look at multiplication first because uh, unlike, say, with integers, like whole numbers, um, multiplication is actually easier than, say, addition. Like when it comes to multiplying here, all we have to do is simply multiply across the top and the bottom. Because say here, 6 over 11 multiplied by 2 over 7. Like 2 over 7 is basically 2 divided by 7. So we're multiplying by 2 and dividing by 7. So that's why you find the 2 ends up on the numerator and 7 belongs on the denominator because the denominator is where what you're divided by. And so you see we can essentially just multiply across the top, multiply across the bottom, 6 times 2 over 11 times 7, and we get 12 over 77. And then you always want to try and simplify your fractions wherever possible. I mean, this one we can't simplify. So how do we do it with division? It's the same thing, but it gets reversed. So 2 divided by 9 times by, divided by 5 over 6, you essentially just times in by 6 over 5 instead. So you take the reciprocal of that fraction that you're dividing by, and you can then multiply by it, and essentially the same thing. Um, So now we know how to do that. Just multiply across the top and the bottom, and we get 12 over 45. Like I said, always simplify. You see here, there's a common factor of 3. We can take that factor of 3 out, and it will cancel out, and we're left with just 4 over 15. Now, where it gets a little bit more tricky is when you have, say, something like addition, like this. And in order to add two fractions, you need the denominators to be the same. And once the denominator is the same, you can basically add across the top. Because, say, if I had something like, 1/5 plus 3/5, it makes sense that would be 4/5. You imagine taking like a pizza and I cut it into five equal pieces. One of those pieces plus three of the pieces will be four pieces in total. Like it's kind of like that way of thinking. We can't just add across the numerator and the denominator. That doesn't work. So what we have to do things like this where we try and get them both to a common denominator. And one way you can always do that is say if I times 1/3 by 8 on the numerator and denominator, and 5/8 I times the top and bottom by 3, then you can see on the bottom we're basically getting 3 times 8 or 8 times 3, which is the same thing. So if we calculate that out, you see it'll both come to 24 on the denominator. Now we haven't actually changed either of these fractions. The values are still the same because we've done the same thing to the top and bottom of each. So now we can just add nicely across the top and bottom. We get uh, across the top, sorry, and the bottom's just going to stay at 24. So, and the same thing applies with subtraction. You need to get the denominators the same first, and then you just subtract across the top. So it's like the exact same thing. So if I was doing, 15 over 24 minus 8 over 24, it would then just be 7 over 24. It's same thing. Um, right. So now let's look at things like this. This is what's known as an improper fraction. Like a proper fraction is one where the the numerator is the smaller number. So you have, say, something like 2 over 3 would be a proper fraction, whereas 14 over 3 here is not because it's the numerator is bigger. So how would we simplify this, or perhaps convert into a mixed fraction is one way we simplify. So I want to remind you of, say, how we did long division before, and where sometimes you'll divide and you get a remainder left over. That remainder still needs to be divided by what you was dividing by, in this case 4. So this, if I wanted to put this as a mixed fraction, this would actually be 68 and 1/4. 68 and 1 over 4, because that 1 still needs to be divided by 4. And so we can do the same thing with numbers like this, but if the numbers are small enough, then you might not have to actually use long division, but you can if necessary. Um, Here, you might be able to see that the largest multiple of 3 under 14 is 12. So we can split 14 up into 12 plus 2. And this, we've seen like with our distributive laws in the previous lesson, like we can split this up like this. And so 12 over 3 is 4, and the 2 over 3 just stays as 2 over 3. That's the remainder 2 still being divided by 3 there. And we put this as 4 and 2/3. And we put them right next to each other like that, which I know might be a bit confusing compared to, say, when we have something like a number and a symbol, like what we saw last time, where with surds, we had a number times by a square root. You put them next to each other, and that implies multiplication. Whereas here with mixed fractions, where you've got essentially two numbers here next to each other, that means actually they're adding together. It's 4 and 2/3, not 4 multiplied by 2/3. Um, so a bit of arithmetic. When we're trying to add two mixed fractions like this, it's not too bad because we can just separate them out like this, the whole part and the fractional part, add together the whole parts, add together the fractional parts, and we'll get 6 plus 13 over 15, or 16 and 13/15. Those two fractions we can just add together in the same way we did before. So 2 over 3 times the top and bottom by 5, 1 over 5 times the top and bottom by 3, and you'll get 10 over 15 plus 3 over 15, which is 13 over 15. When we have addition, multiplication or division, it's a bit more complicated. So we have to convert them back to improper fractions. We can't do it in this form. So we can put them back to improper fractions. So 4 and 2/3. So we think, okay, what divided by 3 will get to 4? Well, it's 12. So 12 over 3 gets you 4. So we could put 4 as 12 over 3. So we've got 12 over 3 plus 2 over 3 gets 14 over 3. So that's how we can essentially convert back to an improper fraction. Same thing with the 2 and 1/5. What divided by 5 gets to 2? Well, that's 10. So 10 over 5 is the same thing as 2. So we got 10 over 5 plus 1 over 5 gets 11 over 5. So that's how we put those into improper fractions. Now we know how to do this division. Just flip that second fraction and we can multiply instead. Multiply across the top, multiply across the bottom. Then we want to break out into a mixed fraction again. So we need to convert back. And we can see the largest multiple of 33 less than 70 is 66, isn't it? 66 over 33 is going to be 2. And then we've got the 4 over 33 left over. That 4 remainder still being divided by the 33. So that's how we would do um, that division with mixed fractions. You know, it's just a bit longer, but we can use all the same techniques we've just seen. So let's move on to decimals now. So decimals, like we saw last time, like with place values, how we construct a large number like this. Well, we can always continue to the right, and instead of going up in powers of 10, we're now going down in powers of 10. So this is now your tenths. So 10 to the minus 1 or 1 over 10. This is your hundredths, so 1 over 100 or 10 to the minus 2. Similarly, 10 to the minus 3, 10 to the minus 4 is your thousands, tens of thousands, hundredths of thousandths, I should say, not thousands, thousandths. So it's 1 over 1,000. And then finally millions. That's 1 in a million. So uh, when it comes to long arithmetic, sometimes things are the same, sometimes they're different. So with addition, it's actually the same. So you can just, again, line up your place values and then forget about the decimal point. You know, we could just add down the columns again. This gets to 10, carry the 1, 4 plus 3 gets 7, plus the 1 gets 8. And you just put your decimal point in the right place. And it works perfectly fine. And the same thing with subtraction. You remember how you have to borrow a value from the next column, perhaps if it's going to go negative. But again, the decimal point makes no difference. Where it does make a difference is with multiplication and division. And well, let's see what would happen if we didn't make any changes. Say if we just tried to do it the way we've done before. So we start with the 9, multiply by the 1, multiply by the 5, we get 45. We're carrying that 4, so do 9 times the 3 plus the 4 gets 31. Same thing again, we need to put for the 2, we need to put down the 0 first. Then we do 2 times the 1, 2 times the 5 is 10, carry the 1, 2 times the 3 is 6, plus the 1 is 7. And if we add down the columns again, we get this. Now you might be able to see that's not really right. We've got 35.1 times 2.9. That's not really going to come up to 1,000. It's a bit much. So what's gone wrong there? Well, let's look at essentially the exact same long multiplication here, but we've forgot about the decimal points, and we're just doing 351 times 29. This calculation is correct, and it does come out to 10,179. So it's all the same digits, just, we've removed the decimal point. And right, so what we need to do is compare this calculation to the one we did before. And so we had 35.1 before, and we've made this 351. So what we've done is we've essentially multiplied it by 10, haven't we? We've moved that decimal point 1 to the right, multiplied by 10. Same thing with the 2.9, we've multiplied that by 10 to get to 29. So the final answer here that we've got in this example is going to be 10 times 10 times bigger than the actual answer we want. So it's basically 100 times bigger. So if we take this answer here and divide by 100, so basically shift decimal point 2 to the left, we will then get our answer, which you can see just down there. 35.1 times 2.9 is 101.79, which makes more sense. If you think about it roughly, 35 times 3, it would be around about 100. And so, the reason why that happens is because when you're timesing by decimals, like say tenths or hundredths, you're actually making the numbers smaller. And so when we carry digits over, we're carrying over to the left. And so it's like we're assuming the number gets bigger when actually it's getting smaller. And so it can mess with the place values a bit. And so this is the way we need to do it. You do the calculation with no decimal points and then see how many times bigger, like how many powers of 10 bigger is that answer, or smaller perhaps is the case. And you just adjust accordingly. So if we try the same thing with division. So we have something like this, and we're trying to do 502.36 divided by 1.9. Again, forget the decimal points and we do the division as normal. Here, so we're dividing by a two-digit number. So it's a bit more complicated, but the same rules apply. Like we do 50 divided by 19 gets 2 with a remainder of 12. Make sure, yeah, you put those place values in the right place. Like we're seeing that 5 zeros are 50. So if we have a remainder of 12, the 1 and the 2 need to go below the 5 and 0, respectively. And so now we drop down the next 2 because we can't divide 12 by 19. Do 122 divided by 19 gets 6 with a remainder of 8. Drop down the 3, do the division again, we get 4 and a remainder of 7. Bring down the 6, we get 4 again with a remainder of 0. So that division is correct there, and you do get an answer of 2,644, but that's not the calculation we want. So we need to know how to adjust this to get the actual calculation we want over there on the left. So we again look at these numbers. See 502.36, we had to times by 100. You know, we shifted that decimal point 2 to the right to get to 50,236. And the 1.9 we times by 10 to get to 19. So does that mean then the final answer we got here is 1,000 times bigger? Like 100 times 10? No. You've got to be very careful of the operation that we're using. So if I put it like this as a fraction, you know, 502.36 divided by 1.9, we're timesing the top by 100 and timesing the bottom by 10. So we're times it by 100 divided by 10, which has a net result of essentially multiplying by 10. So that final answer we got over there, we actually have to divide by 10. And so the actual answer we want is 264.4. So this is how we would deal with decimals when it comes to multiplication and division. A slight change, but not too bad. So finally, let's look at percentages. There's not really much to say about percentages in themselves because um, they're more just a way of presentation. I'll talk about that in a sec. But at first, what a percent actually is, it's a standard way of expressing a proportion as simply just a number out of 100, like per cent, per height. So cent means 100, like century is 100 years, centipede has 100 legs, cent means 100. So per cent means out of 100. And you can kind of see this in the actual percent symbol. You know, it's essentially out of 100 like that. So this is a good, like I was saying, it's more for presentation because it gives us a good way of comparing different proportions. Because say if I gave you two fractions like, you know, 5/8 and 4/7, and I said, okay, which one's bigger? It's hard to really tell. Whereas if I gave you, say, 50% and 60%, I say, which one's bigger? Well, obviously it's the 60%. You know, whatever number is bigger is going to be so it makes it easier to compare things. Um, and yeah, like I said, easier for presenting, especially with things like statistics. We'll see that, you know, way later in this course. Um, but we don't really use them for calculations. Like you see with fractions, say if we wanted to do a quarter of a quarter, we just do a quarter times a quarter and it gets 1/16, which is correct. Or say with decimals, if we wanted, again, a quarter of the time of a quarter, which a quarter is a decimal is 0.25. So we just do 0.25 times 0.25, gets us 0.125. Again, that's correct. But we do a quarter as a percentage, that's 25%. 25 times 25 is 625. The answer there is not 625%, it's actually 12.5%. So it's way off there. So we can't actually use percentages for calculations. They're for presenting. If we want to do calculations, we always have to convert percentages to either fractions or decimals, depending on what we have available to us. Like if we've got calculators, it's normally easier to just use decimals. If we haven't got a calculator and we need to do it on paper, normally fractions better. But it depends on the context. And with practice, you know, you'll just to be able to determine which one actually is going to be easiest. And we always want to take the easiest path, don't we? Like no need to make things more difficult for ourselves. So let's look at that. How do we convert between different types? So here's all the possible different conversions we could have. So percentage to decimal, decimal to percentage first. Let's look at that. And which I would consider the easiest one. So because remember, percent is just basically per 100. So it's basically doing 63 divided by 100 there. And dividing by 100, there's a reason why we pick 100 because we have a base 10 counting system. It just results in essentially shifting the decimal, you know, the place value. So we shift 2 to the right, becomes 0.63. And so that'd be, you know, decimal form of 63%. And likewise, we can go the other way quite easily by just shifting the digits the other way. So 0.17 becomes 17%. And so just by shifting the digits back and forth, we can easily convert between these two, as long as you make sure you convert in the right direction. So decimals are essentially going to be out of one, percentages are out of 100. So the percentage will be the bigger number. So if you've got 0.17, and 17%, you see the percentage is going to be the bigger number. You just got to be careful with, say, more complicated decimals like this, but the same rule applies. Like, okay, so we need to times this by 100 to get to a percentage. So we shift decimals places, like 2 to the left, and we get 8.04%. Or say if we get something like this, I said, decimals are out of 1, but you can have, it can go greater than 1, and that would essentially be equivalent to a number greater than a percentage greater than 100%. So this, again, the same thing, shift the decimal places and you get 1.571 as your decimal for that. So let's take a look at percentages to fractions and vice versa. So if we have a percentage here, 48%, like we already saw a moment ago, you can essentially put that like this because percent is per 100. So it's just 48 out of 100, simple. And then it's just a matter of simplifying that fraction. So here, this can simplify to 12 over 25 because the top and bottom can be divided by 4. Going the other way can be a little bit more complicated. 3 over 5. So remember, percent is just out of 100. So we need to try and get the denominator to 100 here. And this isn't too bad because we can just times the top and bottom by 20 and we get 60 over 100. So that's just 60%. But it's not so easy when you get 6 over 40 like this. Because what do you times 40 by to get to 100? It's not so straightforward. You might be able to see it's 1.5 or lots of 40. But if you can't do that, sometimes these kind of calculations, it's better to take a step forward before taking a step back, sorry, before taking a step forward. So here, if we simplify this to 3 out of 20, and then you can see 20, we can multiply that by 5 to get to 100. So we times the top by 5 as well and we get 15. So yeah, 6 over 40. We can simplify by dividing the top and bottom by 2 and then times the top and bottom by 5. And you see, that's essentially like times it by 5 divided by 2, which is 2.5. So 2.5 lots of 40 gets you to 100. And yeah, once we've got it to that form, it's easy. It's just 15%. So last case, we don't really have to worry so much about fractions to decimal because we've already seen that with the long division. So like in last lesson, where if we have a number divided by another number, which is what a fraction is, we can just do our long division, and we tend to use that for decimal for whole numbers, sorry. But same thing with decimal numbers. Like I said, you just put in the 0.0000 after the number, and it allows you to continue that long division until you hit a remainder of 0, or it starts to repeat. So if you can't remember that, take a look at what we did last time to see how that works. So we just need decimal to fraction. So we can take something like 0.4. We can essentially we need to shift, to make this a whole number. We can shift it by 1 to the left, like so. That's essentially like multiplying by 10, isn't it? So if we multiply by 10, this would become 4. So 4 divided by 10 will get you to 0.4. So you see, using that logic, you can get it to a fraction by just looking at how many digits there are after the decimal point. And, again, just simplify as usual. And then say with something like this, we can do the same thing, that this is essentially going to be 64 divided by 100, isn't it? Essentially like the same thing we do with percentages, and then just simplify that fraction. And then finally, say one like this, a little bit more complicated. It's just we're shifting 3 digits. So we're dividing by 1,000 here. And you can see 1,025 shifted decimal point 3 places will be 1.025. And that we can simplify to 41 over 40. A bit more complicated, that one. You typically would probably, would see more just 1 or 2 digits after the decimal place. Right. One thing we've got to look at is, say, recurring decimal numbers, because that's a bit more complicated. So that's something like this. Say if we have 0.3 dot or 3 recurring, what that means is basically this. It's 0.3 3, 3, 3, 3, 3, 3 going on forever. And so we can't really use that trick I just showed you where like there's no number of tens I can multiply this by to then make it a whole number because those threes go on forever. So you just be times them by 10 to the infinity, that's just not going to be possible. So we have a little technique on dealing with this. We need to cancel out that recurring part. And how we typically do that is like, okay, we look at this. This is one times our number, obviously. Um, and because we've got one recurring digit, what we want to do is shift it by one place like this. So I times it by 10, and so it becomes 3.3 recurring. All digits are just shifted one to the left. Then if you imagine subtracting the larger one from the smaller one, you can see all those recurring digits, which are the same in both, are going to cancel out. Just imagine doing like a long subtraction there. They're all going to cancel out. And so you basically just got three. And that three is nine times that number. Because if we have 10 times the number minus one lot of the number, it's going to be nine times the number. So our original number is going to be 3 divided by the 9. So there you go. We have it as a fraction. It's 3 over 9, which we can then simplify to 1 over 3. And you might have already known that with this one, 0.3 recurring is basically a third. Um, so what you typically get for these kind of problems, this is quite an advanced problem, like, higher grade, um, would be something like this. And we need to try and get that as a fraction. But you can use the same technique. So when you have 2 points like that, what it means is that the digits between those two are what are repeating. So we've got 1.3 and then 594, 594, 594, 594 over and over again forever. Okay, how do we deal with that? So again, we see that's our number, one lot of our number. And we need to shift it by 3 places because we've got 3 recurring digits. So what we do is we times it by 1,000. That's going to occur, shift it 3 digits. And now again, perhaps you can see from the hundredth column onwards, they're both the same. And so if we do one subtract the other again, after a certain point, that hundredth column onwards, it's all going to cancel out and we've just got zeros. And that is going to be 999 lots of the number, isn't it? Because 1,000 minus 1. So we can put that as a fraction now. We've got that divided by 999 is our number. So now it's just a matter of simplifying this fraction. So if we times the top and bottom by 10 to get rid of the decimal, and then we try and simplify this. And this is quite a tricky one to work out and simplify. This is about as hard as it could get. So, but you could be asked questions like this. Like I said, this is top like sort of grade 8, 9 sort of problem. But yeah, that's it. So let's finish up with a did you know? So did you know that some decimal numbers actually go on forever and never repeat? Now, this is something you will encounter a little bit in your GCSE. So one of the most common ones is this number pi, otherwise known as Archimedes' number, which is all to do with circles, geometry, trigonometry, which we will be moving on to in later lessons. And so you will see this number. And this is a number where not only do those digits go on forever, but they never repeat. And a key property of that is we cannot represent it as a fraction like we just did with the recurring numbers. Recurring numbers, they will always have a fraction form. These numbers don't. So pi is one example. Like we've seen as well is with roots. The root of any number that isn't a square number, like if it doesn't come out to an integer answer, it will always come out to an irrational number like this, where it just goes on forever. Another example is this number, which is the golden ratio. We'll see that a little bit more when we take a look at ratio, which is used a lot in design and we see it a lot in nature as well. And another really important one is this one known as Euler's number, which is denoted by a little e, which you won't really see at GCSE level, but you will see it a lot at A level if you decide to do A level math. It plays a very pivotal role in calculus. So leave it there. Here's your takeaways for today. Again, make sure you fully understand this before we move on because we're going to keep building upon things. So you want to make sure you leave no stone unturned. Right. So next time we're going to be looking at approximations, rounding, error management because so far we've only been looking at like whole numbers and proportions where we calculate things exactly. But sometimes we can't always do that, or it's not advisable to do that, and we just do things roughly. And we're going to look at how you deal with that. So, to see you there.